Okay, so for the last session, we're going to get to what we do here at JLab, talk about the GlueX experiment and how it fits into this picture. Again, I'm primarily working on GlueX, so that's why I tell you more about it. But there are a few things from class 12 I'll point you to, and there's lots of interesting spectroscopy going on there as well. Those are the two main halls B and hall D, that are doing spectroscopy at the lab. Yeah, so let's talk about that. In 2017, JLab started running it with 12 GeV electron beam. And so that's the racetrack accelerator that you heard about yesterday, and the experimental halls that you'll get to go visit hall A later. But in halls D, where we have a real photon beam, and hall B, where we have the class 12 detector, we're using these photo production processes to try to look for exotic mesons. And I'll try to show you where we're at with that today. From sort of a historical perspective, these pion beam experiments, like the one from COMPASS we've been talking about, have been going on for 30, 40 years. So there's quite a history of doing pion beam spectroscopy. From the photon beam perspective, our best competition for GlueX before we started running was mostly happening in bubble chamber experiments in like the 1970s. So people just haven't looked in photo production for a while. And so that's one reason why GlueX is a good way to try to search in spectroscopy. So what do we do in hall D? We have what we call the GlueX experiment, and I talked a little bit about earlier. Where you bring the electron beam from the CBAF accelerator, you allow it to hit a diamond wafer, and then we tag the scattered electrons in a separate dipole magnet. And what's not shown to scale here is there's 75 meters of space between where these photons get made and where they hit protons inside of the detector. So the great thing about that is all the radiation you produce when you scatter electrons from a diamond wafer is all shielded before you get to the actual experiment. And so we really have a very clean, pristine beam of photons by themselves hitting the target. The other aspect of GlueX I'll point out is that we have this large acceptance. So it's a forward angle spectrometer. It's a solenoid that has full 2 pi azimuthal coverage. And we measure angles all the way from about 1 degree relative to the beam direction up to about 120 degrees in polar angle. So that means, especially when we're looking at these decay distributions, you want to measure those spherical harmonics, you want to have coverage across a wide range of angles so you can see that angular pattern. And that's why we designed and built GlueX the way we did, with large acceptance for both charged particles. So we could look at things like the charged pion decays that were observed at COMPASS, as well as neutral particles. So we could look for things like ETAs that decay to 2 photons. And I'll try to show you some examples of both of those. This is what the diagram of the experiment looks like. In terms of the beam itself, I'll tell you a little bit about its structure because it's important for how we do the analysis. This diamond has a particular property that when you scatter electrons from it, they can scatter coherently so that you get linearly polarized photons. So you are probably familiar with things like circularly polarized photons, that you get right-handed or left-handed helicity states when you have the helicity of the electron that produces a photon in that case. The linear polarization is perpendicular to the direction of the photon beam. And that allows us to have a new production plane angle we can compare to the decay angles of the particles. And so that allows us to actually do things like separate different kinds of production mechanisms. And I'll tell you a little more about that later. But this coherent Bremsstrahlung process allows us to measure or to produce what we call the coherent peak. So this is the flux of photons as a function of photon beam energy. If you just have a regular piece of aluminum in the beam, you get something like this black spectrum. But if you line the crystal orientation of the diamond up just right, you can get coherent Bremsstrahlung, which produces a sharp spike in the photon beam energy. And we can place it essentially wherever we want, but we put it at about 9 GeV. So we get not quite a monochromatic photon beam, but a pretty focused energy range for our analyses. So think about having a 9 GeV photon beam, which has polarization of those photons that are linearly polarized at about the 30 or 40% level in this region. So we can use those polarized photons to do our amplitude analysis. I'll tell you about that later. And that's that 75-meter distance between where we make the photons and where they hit the detector. Oh, this is a movie that isn't going to work in PDF. So let's see, maybe I can just share my slides. You stop the share here. I'll try to share this. Keep it. So I think if you can move the Zoom screen to the right.
That's what you're worried about. Sorry, yeah, that makes sense.
Then it should.
Is this about a link? Is this the Jupyter one?
It was the keynote slide I wanted to show. Okay, so this is the construction of Hall D. We don't build new detectors here all that often or new experimental halls, but this is hopefully an example of what it takes to put together an experiment like GlueX. Many of these experiments are planned for something like 20 years before they start actually taking data. The video that you're watching here is about a minute long, which has something like 5 years worth of construction time. So that picture that I was showing you earlier of this large solenoid is this red and green thing. And inside of that is where we have the liquid hydrogen target. So many of you are possibly working on building detectors at your home institutions or coming to the lab and working on those. These are examples of, or what you see in this picture are examples of folks bringing their contributions to the GlueX experiment. We tend to run a little differently than some other halls where you might bring in a dedicated piece of equipment for like 6 months to run your experiment and then go home and analyze your data. GlueX is rather stable, meaning when we put it and install it, we run with that experiment for years. And I'm going to tell you about data we've collected since 2017, and we tend to run those experiments for long periods of time. So just a picture of what it really looks like in the hall, because you won't get to go see it on your tour this week. But when we take a look at this picture of the solenoid, I'm going to show you in a minute what an event looks like in our detector, and hopefully that gives you some sense of what the reactions look like that we see. So to orient you in terms of our experiment, this is the main GlueX detector. The photon beam is coming along this direction, and inside of this, where this drift chamber is where the liquid hydrogen target is. We produce a reaction where a proton and 2 pions are produced, and they go forward through the detectors. We measure their ionization inside of the chambers. And over here, you can see a downstream view. So here you're looking down along the beam line going into the page, and you see the curved trajectory of the tracks as they go through the detector. So if we were to look for a reaction that had a photon beam hitting a proton target, making a pi plus, a pi minus, and a proton, this is an example of one of those events would look like. And when we're running the experiment, we're producing these collisions or we're detecting the collisions, triggering on them about 100,000 times a second. So we're taking big data sets, something like petabytes of data per year, to try to unpack these individual kinds of events, but on a large scale. So that's a bit of the detector piece. And what I'm going to try to tell you, yes, question.
Is there any specific trigger mechanism for identifying such reactions? Because it's different from other halls.
Good question. Yeah. So the question I think is there a specific trigger that allows us to capture these kinds of events in the GlueX detector? And the short answer is no. So GlueX has what some people refer to as a wide open trigger. So we have calorimeters, which measure the deposits of energy of different particle types. So let's go back to the diagram. So this thing called the barrel calorimeter in yellow and the forward calorimeter in this forward region essentially measure the deposit of energy of all different kinds of particles, charged pions, but also photons that deposit all their energy. And we just set thresholds on a minimum amount of energy in the barrel calorimeter, and the forward calorimeter is our trigger. So our intention is to record every interesting photo production event, which is quite different, as you say, from other experiments that need a very selective trigger. So that means we tend to run with lower beam currents than many of the other halls. In some halls, you're thinking about hundreds of 100 microamp kind of currents. In GlueX, we think about 100 nanoamps is actually a pretty big current. So the most I think we've ever run with is like 300 nanoamps of current in Hall D. Okay, so rather different setups from some of the other experiments. Other questions about the experimental setup? Okay, we can come back to them if there are. Okay, so let's talk about how we're going to try to probe these exotic mesons in GlueX. So this is that same lattice QCD calculation of those exotic quantum numbers. And we're thinking about now replacing the pion beam that COMPASS had with a photon beam. So you come in with the quantum numbers of the photon, a 1 - system. You're going to need some quasi-particle exchange. Those are those Reggie theory diagrams we were talking about earlier, to allow us to produce a hadronic system X and some recoiling nucleon. That might be a neutron or a proton or even an excited delta kind of system. But we're thinking about these kinds of diagrams and then looking for the X particles and how they decay. And we want to measure those quantum numbers just like COMPASS was measuring them with these amplitude analyses. So thinking about the angular distributions of that decay. So going back to that picture from COMPASS, we can look at, this was their data on a pion beam coming in, making an eta pi minus system, and then looking at the decay of that eta pi and asking how much does it look like one of these different spherical harmonics, the S wave, the P wave, or the D wave. And what we said, or what we were talking about earlier, was this thing looks specifically like one of these D waves, this magenta one, the D1, that's a pretty obvious feature in the spectrum. So the first question, or one of the first questions we were asking with GlueX is, do we see the same thing in our data? So let's try. What do we do when we look at in GlueX? Well, we replaced our pion beam with a photon beam, but we're measuring the same final state particles as COMPASS was. In eta, in our case, it decays to 2 photons and a pion. And then at the bottom, because we have a charge exchange process, we're making a charged eta pi system while we started with a neutral photon. We've got to have an extra unit of charge down here. So we actually measure a delta plus plus baryon at the recoil at the bottom vertex. But we're going to mostly ignore that for now and just focus on the eta pi system. So we can plot the mass of the eta pi system, and we see this very strong peak at around 1.3 GeV. That's the A2 1320 that matches exactly what COMPASS saw. But interestingly, we see in the lower mass region another contribution. And there is known to be a particle with an S-wave set of quantum numbers, the A0, that seems to be produced in photoproduction and not seen in the COMPASS data. So can we then try to learn something about these things, not just by looking for bumps in the spectrum, but looking at these angular decay distributions, just like COMPASS did? And so in the GlueX experiment, we have the ability to say something about not just the quantum numbers of this decay particle, but also what the exchange was in this interaction. And that's because we have this linear photon beam polarization. So I'll try to describe that in a minute. But let's first start by looking at this angular decay. So this is the plot to compare with the previous one from COMPASS. So look at this angular distribution and keep it in your mind, and then go 2 more pages to the GlueX experiment. It looks like, in fact, with GlueX, we see the same D wave as the dominant feature. It has these 2 lobes in the intensity where we see a lot in excess of events, and that matches pretty well with this D1 wave that COMPASS saw. So check the box 1, we get the same answer for a well-known resonance as somebody else. And we see down here another feature around the A0. Interestingly, that doesn't seem to have these 2 lobes in the angular distribution, but if it's an S wave, it should look rather flat in that angle, and it does seem to be kind of continuous across the mass range. All right, so we have the ability in GlueX to see similar things. And in fact, if we do what COMPASS did and we try to measure what is the intensity of different contributions as a function of mass, so in each one of these bins, extract the intensity of the different contributions, we see that they map really well onto one strong wave, this D1 wave that happens to be the strongest amplitude that contributes to the A2. Now, importantly, with the GlueX data, we can measure what's known as the reflectivity or the naturality of the exchange. That basically just tell us about what the quantum numbers of the exchange particle that's required to be here is. And the little plus sign that goes with each one of these, the bottom index is the M projection of the D wave, and the top indicator, the plus and minus, tells us about whether it's a natural or an unnatural particle. You can ask me what that means a little later, but this minus sign means an unnatural pion exchange. And so we expect that the biggest contribution to this production is really the exchange of a single pion that makes this A2 particle. So we're on our way with understanding the GlueX data to be able to describe things that have been seen by previous experiments. And then, of course, we want to go look at where the exotic stuff is. So one of the ways we're doing that is to look in this decay mode of the eta prime pi. So if you remember back from COMPASS, their intensity as a function of this angle and mass showed something that looked kind of like the A2 in the lower mass region, but it got kind of fuzzy in this region around the 1.6 GeV range. And that's because in this region, there's an interference between the D wave, this conventional set of quantum numbers, and the exotic, the P wave. So if there's interference between the pi1, this exotic state, and the conventional A2, this odd and even L waves, then you should get an asymmetry, sort of a forward-backward asymmetry in the intensity as a function of this angle. So it won't look just like one of those spherical harmonics, but it'll be some complex interference pattern between the 2 spherical harmonics. And what we see in the GlueX data now as a function of this eta prime pi mass is what looks like that same interference pattern. So we're in the midst of trying to understand that and see if we can map on to what was seen from the COMPASS experiment. But we think there's evidence here that we're seeing the same pi1 1600 from the GlueX data. So that's sort of where we're at with the exotic waves from the GlueX experiment. What I'd like to spend a couple minutes on is for you to get some practice with this yourselves. So there's another collaboratory workbook that's linked here on the slides, but also is linked directly from the Indico page. So grab your laptop, open it up, and pull that up. And we'll talk a little bit about how these interference of amplitudes work that produce this kind of system or kind of angular distribution that we see in experiment. So take a minute to pull that up and I'll do the same and then we can talk about it. Okay, I should be over here. Okay. Okay. Okay, so there are two, the link is a little different than yesterday. So what we had yesterday was called the hadronic resonance exercise, and it was just this mass-dependent function for the Breit-Wigner. So we had this amplitude that had a complex contribution in it, and we showed that when you did that, you could get these kinds of complex phase motions that as a function of mass, as you go around this Argon diagram, the phase is changing. What I'd like to show you today is that we can actually build in a model that has more than just a mass dependence. We can build in a model that has a dependence on the angles of the decay, and those tell us about the orbital angular momentum in the decay. So instead of building up a model like this intensity that just has a dependence on m, in the new file that should be called something like resonance exercise angular. Reconnect. So this is the one linked on today's with today's slides. It should be angular mass interference. Are people able to open that and it's working okay? Okay. So let's go back to the beginning of that one. It has all the same stuff at the top, but starting with extension 2, it has an angular dependence for the SP in the D wave. So let's talk about what that amplitude looks like when we start to build in the fact that there are different orbital angular momentum contributions. So we don't just have a mass dependence, but we're going to have a dependence on this decay angle theta. That's essentially the angle of the eta relative to the photon beam. So how is the eta produced relative to the direction of the initial incoming photon? And we can write that in terms of the Legendre polynomials for a given L. Where for a spin 0 or L equals 0 and S wave, we get 1, we get an X dependent linear dependence for L equals 1, and this quadratic dependence for L equals 2. And so we're gonna have different expectations if we have an S wave, if we have a P wave, this L equals 1, or if we have a D wave, which would be this A2 1320. So there's a nice figure there that shows essentially this Legendre factor for these, you know, the flat wave, the linear wave, or the quadratic. And what I'd like to go through in a little bit of detail is how those, that we don't just look for this particular set of intensities, but we have to deal with the interference between those contributions. So what does the actual mass-dependent amplitude look like that you might describe the data with? You need to deal with something that has both, so it's an L-dependent amplitude. So if you've got a L equals 1 exotic wave, that should be different from an L equals 2 conventional A2 meson. And so you've got to have that L dependence, you need a mass dependence, and you need this dependence on the angle. And so you can build in a Breit-Wigner, that's the mass-dependent part of the amplitude, a Legendre polynomial for the angular dependent piece, and then a phase, which is an angular or a complex coefficient that gives us the ability to measure this interference between the different amplitudes. So our model is going to be a sum of amplitudes like this for different L's, different particular quantum numbers, different spins. And we're going to build in some mass-dependent model for, let's say, the A2 has a mass of about 1.32, and the Pi1 1600 has this mass of 1.6. And so you can make those these Breit-Wigner functions and the Legendre functions. And you can start to play with these things. So one of the first plots in here says, what happens if we have at a given fixed mass of like 1.3 GeV, we're dominantly in the mass range of the D wave. And so if we're in at one point at the peak of the A2, it's going to look essentially just like the intensity is dominated, the square of the intensity is dominated by just the D wave contribution. But in the model, you can choose to plot that at a different mass. So in places where you have this M0 quantity in the Python workbook, you can replace that instead of the mass of the A2. Let's ask, what do the intensities look like in the mass of the Pi 1 1600? So let's put in instead 1.6 GeV. We can rerun that element. And there we can see that actually there's now going to be some larger contribution from the S wave. The D wave is actually really suppressed. There's not very much A2 left out there. And we've got maybe a big P wave contribution to deal with. And so for the analyzer trying to fit their data with this model, they're essentially trying to figure out what are the coefficients, what are the strengths of these different contributions to the amplitude as you change the mass of the resonance that we're trying to study. Okay, so you can spend a couple minutes plugging in different numbers there to see what these individual amplitudes look like. But the more interesting bit is not just what the individual intensities squared look like, but actually what the coherent contributions look like. We have more than just individual waves that are contributing, but we've got interference terms between the S and the D wave or the S and the D wave. And so if we go now here to the more complete model, we're going to add contributions from the S wave and the P wave and the D wave, and they all have that same form that we were looking at before. So we get contributions that look like the mod squared of the individual waves, but we also get all these interference terms. And it turns out when things get complex and we have broad and overlapping resonances, these interference terms can actually be the dominant part of the intensity. It's not just the individual wave contributions, but the interference between them. And so if we look down here at what that looks like, we can plot for a given fixed mass again. You can choose a mass and ask what are the contributions from, say, the coherent intensity when you add all three of them together coherently, or if you just were to pretend like there was no interference between them and look at the incoherent bit. And you can see those shapes look really different. And so it's really quite critical that we have this full complexity of the model built in when we're fitting our data. And again, this is a place where you can plug in different values. So this is at 1.45 GeV. So maybe that's a region somewhere between the A2 and the Pi 1 1600. It looks kind of a mix, but we could plug in there instead. Let's look at 1.6 GeV. There we might expect to have a bigger contribution from the P wave. And things might look quite different, where this contribution has the incoherent is mostly the P wave, but this interference is the thing that we really want to measure as a function of angle. So as the analyzer trying to look at this data, when we want to decompose the different contributions to the intensity, we've got to have this complete model to understand those. All right, so I'll maybe stop there and let people play with this for a minute, and you can ask questions if you have them before we get back to the lecture notes. Great. Good. So what we're after is trying to look at those interferences between this P wave and the conventional resonances and see if we can reproduce this kind of forward-backward asymmetry. And that's basically what was seen in the COMPASS data to tell them there was an exotic. Okay. So these models we were tweaking in the Python workbook are exactly the same kinds of things we would use to try to understand this intensity. And that's one of the things we're after with GlueX. I'll give you another example from the class 12 experiment. So this is a case where different experiments have different capabilities, and so they focus on different kinds of reactions. So class 12 has much better charged particle tracking capabilities than GlueX does. That's just the way it is. They have a magnet that is designed for that kind of capability. And so they can go look for other reactions like 3 charged pions, which was the earlier COMPASS measurement that we were looking at, where they had these 88 waves to describe the data they saw, and they saw a small signal from the pi1. So how can we do a comparison then of the COMPASS measurements to class 12? Well, this is that same variable, the 3 pion mass distribution, plotted for class on the right and COMPASS on the left. And so we see these features like these various A1, A2, pi2, all conventional mesons, and those same kinds of features appear in the class data as well. So these are rather early days. There isn't a full partial wave analysis to try to extract this information from class yet, but they have a significant data set to be able to do the same kinds of measurements there that were done at this. So what are we after then, or what's the bigger picture kind of view for where we're at with the spectroscopy program? We think of this map of the spectrum that comes from lattice QCD, the meson mass on the y-axis and the different columns of the quantum numbers on the x-axis. We've really completed a suite of measurements in the conventional simple known final state measurements at COMPASS and at class. And now we're working our way up through the spectrum of more exotic, interesting things like these A2s and F2s and other things that I was showing you some examples of in our data. But again, the holy grail is sort of going after these exotics and not just the pi1, but trying to look for this spectrum of exotics that could be there. And that's what I want to spend the rest of the talk telling you about is what we're doing across the broader spectrum of the program to search for these exotics. Back to this picture of the exotic mesons. It turns out that lattice QCD predicts more than just this pi1 1600, is where the field of light quark hadron spectroscopy has been focused for a couple of decades. But in fact, we're expecting that there should be strange quark partners to this exotic. And so we shouldn't expect that there's just a pi1, but in the non-net of exotic mesons, there should be an eta1 and in fact an eta1 prime. So heavier versions of the same quantum numbers, but with different quark content. These gluonic excitations aren't just specific to the pion version of the exotic, but there should be similar eta and eta prime versions of the exotic. And there were some early model predictions for how these different mesons should decay if they were to exist. And we're looking at things like eta prime and eta prime pi for the pi1. And when we go to look for what are the things that, that these heavier versions of the exotic should decay to, they essentially all include kaons because they come from strange ionium type systems, SS bar type systems, just like the charmonium systems we talked about yesterday, but with strange quarks instead. So we have an expectation that we can look for a pattern of these exotics with other quark flavors, and this is going to tell us about how these exotics behave. So what are we doing to try to map out that strangeness program? Well, I think I'm going to skip this one for the sake of time. We can try to make connections back to these charmonium-like systems that were observed in the so-called XYZ states that we talked about some yesterday. So if you remember, there are these Y states that are 1 minus minus vectors that are made in E plus E minus. And it turns out that not just in charmonium, but also in the strangeonium mass range, there's evidence for potential hybrid mesons in that spectrum. So this is a measurement from the Bell experiment, which we talked about yesterday, that looks at E plus E minus annihilation. Yesterday, we talked about how they looked at J psi pi pi events. So that would be charmonium plus 2 pions. They also look at phi pi pi. So that would be SS bar, strangeonium plus 2 pions. And in that spectrum, they see interesting enhancements. One of them is at a mass of around 2175 MeV that gets the name Y2175. This is particularly interesting because it's been seen by a few experiments. And there's a connection, or people have made the connection, between what has been seen in charmonium, where they see these structures in J psi pi pi, and this could be the analog of that system in strange anti-strange systems. So could we make a connection between heavy and light quarks in this sense? And the hope would be yes. And if we do, maybe it tells us something about the nature of those states, which are rather unknown still for the charmonium systems. So back to this picture of lattice QCD, we had a question earlier about what differentiates these orange boxes if you have a conventional set of quantum numbers. Well, they are potentially supernumerary, meaning that they are more states in the spectrum than you would expect from a quark model prediction. And it turns out there is no quark model prediction for a state at 2.175 GeV. And so it seems that what has been seen in these other experiments is supernumerary. Now, whether it's a hybrid meson or not, we don't know, but it does appear to be an unexpected state in the spectrum. So what do we want to do? Well, like in other cases, we want to try to measure this in other experiments and learn if we can find the same pattern across different kinds of productions and decays. So a very recent publication from GlueX is in fact searching for this Y2175 in photo production. So how do you do that? You go measure a phi meson, which decays to K plus, K minus, and you measure 2 pions, and you look at that 4-particle system, the phi pi pi mass, and you plot the cross-section, the probability of making that system in photo production. And it looks like a sort of broad phase-space contribution with a couple of humps on top. And we're able to describe that with a sum of a couple of these Bright-Wigner functions that we've used and worked on in the workbook yesterday, that are able to model the data. Now, we don't say it's a unique description of the data, but it certainly does describe what we see in the experimental data points. And this fit actually doesn't agree with the expectation of having a Y2175 that was seen by other experiments. We actually see a structure at around the same place, but it turns out to be with a significantly different mass than was expected from the previous measurements in E plus E minus. So we see these structures, they're new, they appear to be different from the Y2175 seen elsewhere. And so we aren't getting a consistent picture yet between the two different kinds of production mechanisms, but it does point us to trying to dig into this analysis even further. And here we haven't done any of this angular decomposition. We don't know what the quantum numbers of the events we produced are yet. We were just measuring the cross-section. And so one of the things that's coming next is to try to tease out these different amplitude contributions to the intensity, and then we can say more about what exactly is the state we're producing in photo production. So this is really an ongoing story in what we're learning. So how do you do strangeness spectroscopy better in GlueX? Well, and in class 12, it turns out that you need some way to measure these kaons that are produced in your experiment. They look a lot like charged pions. The only difference is they have a slightly different mass. And so we need a way to distinguish those two. And for that, we're building new detectors, or have built already new detectors that are shrink-off radiation devices. Okay. I'm going to spend a couple of minutes talking about how you measure shrink-off radiation, and then we'll wrap up. So how do you want to tell particles that have different masses apart as they travel through the medium? Well, you can look at particles as they travel through some dense material. Sometimes this is a heavy gas. In the case of the GlueX experiment, this is fused silica. And when a particle goes through that material, a charged particle goes through that material faster than the speed of light, it emits so-called shrink-off radiation. And it has a dependence on the wavelength, which is why when you look at pictures of reactors, they glow blue. They have a high intensity of photons emitted in this wavelength regime. But also you can look at the angle of the production of those photons and measure the shrink-off angle. That depends on the speed of light in the medium, as well as the index of refraction of the material. So you get this kind of shock wavefront for the shrink-off angle. And so the detector we built in GlueX that I'm particularly fond of is called the DIRC. It's the detection of internally reflected shrink-off light. And so the idea is you have a charged particle come in, it emits these shrink-off photons at a particular angle inside of the medium that's governed by its momentum and its mass. And then the fused silica bar that's about 4 meters long acts like a waveguide that you get total internal reflection of the photons inside the bar. And so then you put a bunch of detectors several meters away, and you can measure where they are detected on those sensors, and you can reconstruct what the angle of the shrink-off radiation was. This isn't a new idea. People did this in the Babar experiment at SLAC. Being cheap nuclear physicists, we decided to recycle what they used and are using their equipment in our experiment. So the way Babar set it up was to have a barrel of these fused silica bars around any ± annihilation point. And then they would measure these rings in their detectors and be able to measure the shrink-off radiation angle in the rings that they observe in those detectors. And GlueX, so Babar finished data taking in 2008. And in 2018, we went through a long process of moving these extremely fragile 4-meter long bars in the back of a couple of semi-trailers to Jefferson Lab. It was a quite intensive process where we had all kinds of accelerometers and things to measure small changes in vibrations along the way. Well, they successfully got here without breaking, which we were quite happy about. So what does it look like when you now have kaons that hit this shrink-off detector inside of GlueX? Well, you get these kinds of ring patterns. And if you can measure the shapes of those rings, you can actually infer what the mass or the beta of the particle was. And then we can try to separate things like pions and kaons, and we can look at these kinds of reactions in a lot more detail because we can reject the backgrounds from pions compared to the kaons and really have unique access to the strange quark reactions. Class 12 has a similar device called a RICH, a ring imaging shrink-off detector, and they're able to use that to also isolate these kaons and do new kinds of strangeness spectroscopy in GlueX and Class 12. So I guess I'll finish there. GlueX it has really been running for almost a decade now. I've been here, it's about as long as I've been at Jefferson Lab, we've been running with it. The program's really well underway. We're doing things like other experiments have done in partial wave analysis to extract the signals from these different resonances. And the other thing to say about spectroscopy is that they tend to be rather long-running programs. I'm imagining data we're collecting now from GlueX we're going to be analyzing for at least the next decade, probably more. And that's kind of different from some of the single-purpose focused measurements that happen at Jefferson Lab. So it does behave a little differently than some of the other programs you're going to hear about during the summers. So with that, I'll stop and take questions.
So I was looking at the workbook more, and you had mentioned something about the phase, like the either the I phase and the Brett-Wigner like being related to separating like the S and the P waves. But can you say a little bit more about like how you chose them in the notebook and like what that's physically meaning?
Yes. So go back to maybe a diagram that can help a little bit. So how does the phase enter? Over here, maybe a little better. There are two aspects where the phase become important. One is in the actual the phase that's a free parameter in the model, and also a phase that's built into the Breit-Wigner distribution itself. So when we write down one of these amplitudes, A, L, as a function of M and X, there's two coefficients. There's a CL and an e to the I phi L. So these things are the free parameters of the model. And I could have just as equally written it as AL plus IBL, which was just a real plus an imaginary part, or some magnitude and a phase. So these are free parameters that tell us about the production strength of the given amplitude or the given L wave. So these things nature has to tell us. We don't know what they are. Now there is one other piece which has a mass dependence of, or a real and imaginary dependence, which is this Breit-Wigner sub L as a function of mass. And this thing has the shape that has this phase that's changing as a function of mass, goes from 0 to 180 as you cross the pole position. So there's a combination of this phase, which is a constant for all mass, and this phase change is a function of mass that tell us about the interference between different amplitudes. This thing we have to assume as being part of the resonance structure that's in the model. This thing nature is telling us about, this complex coupling strength between different production mechanisms.
That helps.
So my question is between slides 46, 47, talking about the Y2175. So you said that you didn't see that specific mass in the data. What does that mean for the other 3 experiments that saw it? And I guess the immediate follow-up to that would be what you seem to be suggesting that it's not, that it's exotic, that it's not something that we'd be expecting the standard model. So what would that mean?
Yeah, good questions. So try to see if I understand the question. So we see a structure in these E plus E minus annihilation, and these there are more recent ones which are even more dense. So there's definitely something happening there in E plus E minus annihilation. Here we see a feature in the spectrum, but it doesn't quite line up with the Y2175 mass hypothesis. So the question is, does our non-observation here or observation of something different mean that these are wrong? No, but it does mean that we're seeing something different in photo production than they're seen in these measurements. So this gets back a little bit to what we were talking about earlier with the place where these things peak as a function of mass in different experiments. So what we see is that in the GlueX experiment, what we observe is not a structure that happens to be right at 2175. It's shifted a little bit. Now, could it be that there is some kind of a phase space opening, which is different between the two two production mechanisms, that means that the same kinds of resonance contribution or resonance pole could cause both of those enhancements? Is possible. We don't have the theoretical backing necessarily to say that with the data yet. But I should say that in these other experiments, like at Bell and BESS3, they see other things that peak in this region as well, not just phi pi pi, but also K plus K minus and K short K long that peak in that same region, indicating there may be other decay modes of something like this Y2175 that we aren't accessing yet in GlueX because we're looking at just this 5 pi pi case. So I'd say rather than saying one of them rules the other out, this is more of the beginning to a more complicated story that we need to keep analyzing the data to be able to say more. So it would be nice if we just found a smoking gun to say, yes, it's definitely the Y2175, and that means it's a hybrid. But my experience in this field is the more you dig into the details, the more complicated it gets, and there's not always, sometimes there's more questions than there are answers. But that's part of the fun of doing it.
I'm interested, like, I want to know, like, difference between the class 12 and the GlueX detector. They also measure the Cherenkov radiation, right?
That's right. Yep.
What was the interest behind constructing
Why are they constructed differently?
differently? What is the difference between them?
Yeah, good question. So the two detectors have very different space available and different constraints and what you put into a new detector system. It turns out that GlueX, the place we had the most space, if I go back to the picture earlier, the place we had the most space, let's go here, was in a big gap between the end of our solenoid detector and where we had our forward calorimeter. And in fact, when we designed the experiment, there was originally a detector there, but due to various budget issues, it was de-scoped, is the kind way of saying we decided not to build it. So we didn't build it, but we left space for it so we could build an upgrade later. And that's what the DIRC detector is. So why did we choose that? We needed something that was small enough right, to fit in this region between those two detectors. And it turns out these fused silica bars are very narrow. They're only about 1.5 centimeters wide. And so it fits in a very constrained space. And so that was the reason we put it there. And then all the sensors, the photodetectors, are way out here outside the acceptance. So they could be as big as they want to be effectively. So we were space constrained in how we could fit it into the detector here. Class has a very different system. They have 6 sectors inside of their toroidal field. And if you choose to replace one of the original sectors with a new one, with a ring imaging Cherenkov detector, you can basically use the whole space of that sector. And so rather than putting in a new detector to augment what was already there, like we did in GlueX, they took 1/6 of the detector out and installed this ring imaging detector instead. So they had more space. They could use a different kind of radiating material called aerogel, and they're a combination of aerogel and gas. They're able to do even better in terms of pion and can separation than we could do in GlueX, where we were more constrained in the space limitations.
And one more question, like, what was barrel calorimeter? What it measures actually?
The barrel calorimeter? Sure.
I didn't see in the class 12 that one.
Yeah, so in GlueX, one of the things we wanted from the beginning was to have broad coverage of both charged and neutral particles. So that meant that over the full acceptance, we wanted both to have drift chambers that measure the charged particle ionizations and the neutral particles like photons that we could detect across the full range. So in GlueX, that means inside of the solenoid. So this green thing is a 2 Tesla solenoid. And right inside of it is a little shell of an onion, if you want, inside the can of the solenoid that is layers of lead and scintillating fiber. And so as a photon comes through, it creates an electromagnetic shower, and the light from that electromagnetic shower gets captured by the scintillating fiber, and those go to silicon photomultipliers that are on the ends of these 2 portions of the barrel calorimeter. If you're an EPIC EIC fan, pretty much the exact same design for this barrel calorimeter is what's planned to be used for EPIC in terms of the scintillating fiber, and they're adding some more interesting pixelated readout in different regions, but the same kind of materials are planned to be used there for their barrel calorimeter as well.
Thank you. Thank you for
Any more questions? Okay.